All right, today we're going to learn about gravitational potential energy. So before we do that, let's do a quick review of the concept of work. So if we look at the textbook definition of work, we've got the force on an object times the displacement of the object times the cosine of the angle between the force and displacement vectors. Now, we often think of grouping terms in this way, where we can break the force into its components and only include the component that points either in the direction that the object moves or exactly opposite to the direction that the object moves. And if we have that component pointing in the same direction as the displacement, the work done by that force will be positive. And if that component points in the opposite direction, the work done by that force will be negative. Okay, now if we think about lifting an object, if you were to lift an object a certain height and you started and ended at rest, how much work would you have to do? Well, if we start with the object at rest, we lift at a certain height, and it ends at rest, then the change in kinetic energy there is 0. So that means that the total work done on the object is 0. Now, what forces are doing work? Well, clearly you're applying some force to the object and doing some work on it by lifting it up. And there's also a force of gravity, and gravity is also doing some work on the object. So if we look at the work done by gravity, then that is going to be equal to the force of gravity times the height that the object was moved. And that's going to be negative because the object is moving upward, and gravity is a force that points downward. So those point in opposite directions, so that's going to give us a negative sign. And we know that we can calculate the force of gravity on any object by taking its mass and multiplying by g, the acceleration due to gravity. So the work done by gravity is this negative mgh. Now, because we know that the total work done on the object is 0, that means that the work done by you would have to exactly cancel out the work done by gravity. So the work done by you is going to be a positive mgh. Now, it's useful often to define this as a potential energy, right? So this is the work that you do, rather than changing the kinetic energy of the object, it changes a new concept that we call the potential energy. In general, we can say that the change in gravitational potential energy, which we've written there as PE sub g, is equal to the mass of the object times the acceleration due to gravity times the change in height of the object. So potential energy is a concept that applies to a system, not just a single object. Right? So in this case, when we're talking about gravity, the system is the Earth, which exerts the force of gravity, and the object that's being raised or lowered. So the way that we defined it, raising an object increases its gravitational potential energy, and lowering an object will decrease its gravitational potential energy. And potential energy can be converted to kinetic energy and back again. And so this gets us into the idea of the conservation of energy, where energy can be transferred between different forms of potential energy and kinetic energy. So let's look at this in application. So if we look at this cuckoo clock, and these old-fashioned cuckoo clocks, which don't use electric power, there's a chain, and there's these weights which are often shaped like pine cones. And every once in a while, you have to pull down on the chains and lift the weights up to a certain height. Right? So you have to do a certain amount of work by applying a downward force on the chain, which then lifts the acorn a certain distance, and that gives potential energy to the weight and to the system. And then as that weight then moves downward, that energy becomes the energy, so its potential energy is going to decrease as it moves downward, and that energy then is used to power the clock. That was a simple example where the object was moved straight up or straight down, but you might ask, what happens if you move it at some sort of an angle? Well, we can see what happens in that case by grouping the terms in our definition of work slightly differently. So here I have the force on the object, and I have the d cosine theta grouped together. So now rather than breaking the force into components, I'll break the displacement into components. And only the displacement that's in the direction of the force or opposite to the direction of the force will matter. Anything that's perpendicular to the force will not matter for the amount of work that's done. If we look at that solid blue arrow, if we have an object that's moved up and to the right, a certain displacement d, well, we can break that into a component, right? Because gravity works in the downward direction, and so only the vertical component of that motion is going to matter. So if we're at some angle theta marked there, we can find that component, the dotted line, which is in the vertical direction. That's going to be d cosine theta, and that's going to give us the height. So the component of the displacement that matters is only the height. And that's exactly the term that came in from our definition of work. Generally, you won't have to worry about breaking things into components. You'll just be able to say, well, what's the change in height? And that's all you have to worry about for calculating the work done by gravity. We can apply this to somebody moving into the fourth floor of an apartment building and trying to move a TV in there, right? So if you were going to bring the TV up to that floor, would you rather carry it up the stairs or hoist it by a pulley? If we're only considering the amount of work done, therefore the change in potential energy of the object, it doesn't matter. Whichever path you take has the same change in height. And so therefore the change in potential energy will be the same, and the work that you have to do will be the same. Okay, so let's look at this application problem. So we have a roller coaster that starts, so at the first hill, you kind of chug up to the top on the chain, and then you're released basically from rest. And it drops down to the bottom of that dip, which is a height of 25 meters, and then it goes back up. It goes back up another 5 meters to reach the finish. So the gravitational potential energy that the roller coaster starts with is going to be converted to kinetic energy at the end. Now the question that we want to know is, what is the velocity at the end? Now the nice thing about using energy is that we don't have to worry about the fact that the roller coaster initially goes down 25 meters. We only have to worry about the change from the beginning to the end. Right. So now, when you do gravitational potential energy problems, you always have to pick the point that you're going to call your potential energy zero, which is the same as saying where are you picking your height equals zero. So since we're skipping that intermediate point, we can just go ahead and call our height zero at the end, and say, okay, at the end we have only kinetic energy because the height is zero. The gravitational potential energy will be zero. So at the start, we only have gravitational potential energy, mgh, with h being 20 meters. And at the end, we have kinetic energy only, and that's 1/2 times the mass of the roller coaster times velocity squared. So we can set those two equal to each other. We can see that the mass cancels out, and when we solve for the velocity, that gives us the square root of 2gh, which gives a value of 19.8 meters per second.